For problem 2, x is approaching negative infinity. Okay, so if x is approaching negative infinity, we notice that the numerator has a degree of 1, the denominator has a degree of 2. Because the denominator degree is greater than the numerator degree, we say the limit is 0. Well, that's a pretty easy one. Number 3, as x is approaching negative infinity. Now, there's a little trick when we see an absolute value bar, when we see absolute value bars. If x is approaching negative infinity, if we just make a quick little xy chart, let's just make x equal to negative 100. Okay, so if x is negative 100, the numerator is going to be a positive 100, but the denominator is going to be negative 100. If we made it a negative 1000, if we let x be negative 1000, so we can see we're sending x towards negative infinity, but pretty slowly, negative 100, negative 1000, and we want to do this so we can see a pattern. When we take the absolute value of negative 1000, we get 1000, and when we take the absolute value of, or when we divide that by negative 1000, pen's running out, hold on. Okay, new pen. So when we divide 1000 by negative 1000, just like what we get when we take 100 and divide it by negative 100, we get negative 1. Okay, so all right, so that's one way to find the limit. Limit is negative 1. If we just kind of analyze this a little further, negative 1 billion. 1 billion over negative 1 billion, still negative 1. But the other way to look at this would be if you take the absolute value of a negative number and you wanted to rewrite that absolute value expression without the absolute value bars, you could just replace the absolute value of x with the opposite of x. Now that's kind of tricky, and I know that that's not always something that sits well with everybody, but if you mess with that a little bit, if you just kept putting in numbers, the absolute value of negative 10, let's actually do that. Let me see here. Let's take the absolute value of negative 10. That's equal to the opposite of negative 10, which is 10. The absolute value of negative 100 is equal to the opposite of negative 100, which is 100. So we go all the way down. Oh, the absolute value of x is equal to the opposite of x if x happens to be less than 0. So notice that here's the x, less than 0. So the absolute value of x, there's the x. If x is negative 10, then the absolute value of negative 10 is the same as the opposite of negative 10, which is 10. If x happens to be negative 100, which is less than 0, then the absolute value of x, or the absolute value of negative 100, would be the opposite of negative 100, which would also be, again, 100. So in order to kind of counteract what the negative is inside, if we take the bars away, we have to put a minus sign in front. And so really, you can look at the absolute value of x as a piecewise function. We could say the absolute value of x is just x if x happens to be greater than or equal to 0. Now that equal, we could put the equal up here, or we could put it down there. It doesn't really matter, because negative 0 is the same as positive 0. This is just typically the way we would write it, like that. And so back to the original problem here, number 3. Since x is negative, I mean, you can't get more negative than going towards negative infinity. So therefore, we could rewrite this limit expression as limit of the negative x, or the opposite of x, over x. And here the x's even cancel, and you just get negative 1. So no matter how you slice it, you still get negative 1. All right, problem number 4. As x approaches infinity, we have a rational function here. We have a polynomial that has a leading term of negative x. Leading term meaning the highest degree term. And downstairs we have 5x, 5x to the first power. So the 2 and the 7, those really don't change. Those are totally insignificant numbers as x approaches positive infinity. So we get negative x over 5x, and we could even cancel the x's, and we get negative 1 over 5. Or, again, we can think of that bubble theorem being that we have the same size bubble up on top and bottom, so we peel off the coefficients and now we see negative 1/5 are the coefficients, negative 1 on top and 5 on the bottom. And then for number 5, we have so the bigger bubble is on top, so the numerator has a higher degree, 3, than the denominator. And so we know for sure that the value of the function is either going towards positive or negative infinity. And so all we have to do is figure out the sign. I'm putting a little fraction bar there because the sign of the numerator will be generated by x is approaching negative infinity, and when you take negative infinity and you cube it, you're still going to get a negative. So the numerator will be a negative number. The denominator will be 5 minus, now when you square a negative number, you get a positive number. So negative positive is going to be a negative. So therefore, negative divided by a negative is a positive, and so positive infinity is the value of that limit. Now for number 6, as x approaches infinity, when we have radicals in either a numerator or denominator, we want to simplify things a little bit. We're going to take that plus 1 and we're going to throw it away. Throw away the plus 1 because it is insignificant compared to this x squared, so we can act as if it's not there. Now, the numerator then will be a negative number, negative 4 times infinity, but that's to the first power. The square root of x, the square root of x squared is just x. Really, it's the absolute value of x, but because x is going towards a positive number, really we can rewrite that as x because x is positive. Now, what do we have? We have negative 4x on top. We have a 1x on the bottom. Same size bubble. Limit is negative 4.